going to talk about one-to-one functions and their inverses. First, let's talk about one-to-one functions. You can tell if a function is one-to-one by the horizontal line test. Let's look at these two functions. The function on the right is one-to-one. What that means is for any given y value, there's no more than one x value that corresponds to it. For this y value, there's only one. Let's do that a little better. There's only one one x value that corresponded to it. Let's modify this graph just a little bit. There is an open hole here. That means that point isn't there. So when it comes to this y value, there is actually no x value that crosses the graph, which is everything in blue. Once again, for this horizontal line, for this y value, it corresponds to that 1x. For this y value, it doesn't hit the graph. Corresponds to no x's, which is okay. This is one-to-one, this graph. You can't get more than one y value. More than one x value. For this y value, we get, we get this x value, we get this x value, and we got that x value. That horizontal line crossed in more than one place. It crossed in 3 places. So when it comes to 9, y of, -4 equals 9, y of, call that 1, y of 1 equals 9, and y of, say, 3 is also equal to 9. It's not one-to-one. One-to-one means you never get back more than one x value for a given y. We got back 3 y values. This is not one-to-one. Now, if you consider this function right here, what's in yellow is just the axes, and this is the graph. Y is always equal to 7. Well, there's many x values that give you 7. This x value gives you 7. This x value gives you 7. This x value gives you 7. Assuming this line goes in both directions forever, every x value corresponds to 7. This is not one-to-one. It's the worst example for not being one-to-one. Now, suppose we consider this graph. This graph is everything in yellow. Everything in yellow is part of this graph. So, is this function one-to-one? Well, if you pick this y value, it only corresponds to one x value. If you pick this y value, it only corresponds to one x value. That is, if you draw this horizontal line at that height, it only crossed the graph in one place. For this y value, draw a horizontal line, it only crossed the graph, which is yellow, in one place. For this height, it only crossed the graph in one place. But you know what? For this graph, for that y value, it crossed the graph in two places. As I said at the beginning, everything in yellow is the graph. That blue line crossed the graph here. That is f of this x value and f of that x value gives you this number. Maybe it's 7. Maybe this is -2 and this is 3. But the bottom line is y of -2 is 7 and y of 3 is 7. If y of different numbers give you the same value, it's not 1-to-1. In fact, on this graph, let's get rid of this yellow. I promised everything in yellow would be part of the graph. When it comes to this graph, only one horizontal line crosses the graph in more than one place, and it's this one. Obviously, it crossed here, yellow, it crossed here and here. That is not 1-to-1. Just takes one horizontal line to fail. If there's any horizontal line, it fails. That's one way to pass or to test for 1-to-1-ness. Horizontal line test. Now, there's another definition. If f of some number is equal to f of another number, if that guarantees that a equals b, this is 1-to-1. Definition of 1-to-1. If f of a is equal to f of b guarantees us that a equals b, then the function is 1-to-1. Somebody asked you, is f of x equals 2x plus 3, sorry, not equal to, but is that function 1-to-1? Since we don't have the graph, I would use this definition. Suppose f of a is equal to f of b. For f of a, I replaced x with a, so I should do that there. That is 2a plus 3. That's f of a. And this is equal to f of b, which is 2b plus 3. My goal is to decide or to determine if a equals b. Right now, I have that 2a is equal to 2b. Dividing by 2, I get a equals b. That implies that f of x is 1-to-1. Let's keep this definition up here. So the next problem will go there. The question is f of x equaling to x squared plus 3 1-to-1? So you suppose that f of a is equal to f of b. What does f do to what's inside the brackets? It squares it and adds 3. Okay, I'll square what's in the brackets and denote that I'm adding 3. Square what's in the brackets, add 3. So now I take away 3. And we're going to get closer to determining if a equals b. Well, if a squared equals b squared, that does not imply a and b are equal, because 3 squared is certainly equal to -3 squared. And 3 and -3 are not the same. -4 squared is equal to 4 squared. Those numbers are not the same. But 3 squared or 13 squared does equal to 13 squared, and negative 41 squared does equal to negative 41 squared. Sometimes they can be equal, other times they can just differ by a sign. The best we can say is A is plus or minus B. This implies f of x is not 1 to 1. Why? Because we did not conclude that A equals B. How about this function? Is f of x equaling to x cubed minus 5 1 to 1? Again, since they're not giving us a graph, we should use this other definition. We suppose f of A is equal to f of B. What does f do? What's in the brackets? It cubes it and takes away 5. Okay, I'll cube what's in the brackets and I'll take away 5. I'll cube what's in the brackets, I'll take away 5. Now, I'll add 5. So I get A cubed is equal to B cubed. Now, if you cube 2, you get 8. But if you cube negative 2, which is negative 2 times negative 2 times negative 2, negative times the negative is positive, this is positive, times the negative is negative. And 2 times 2 times 2 is 8. Ooh, we're not going to get the same answer. You never can. If you cube two different numbers, and if you cube two numbers and you get equality, the numbers are the same. You can't cube different numbers and get the same answers. You can square different numbers. 2 and negative 2 are different numbers, but they're equal. They equal 4. I know they're different numbers because every point on the number line is different. Every point on the number line is different. And these two numbers are not the same. But when it comes to cubes, it's okay. If you cube two numbers and you get the same answer, like we're doing here, that means the numbers are the same. That implies that f of x is 1 to 1. If you're given a graph, I give you a graph, say like this, it's easy to tell via the horizontal line test that to get this height, let's say 2, you can have 3 different x values. That's not 1 to 1. When you're given a graph, you suppose f of A equals f of B. And only when you conclude A equals B can you say f is 1 to 1. If you can conclude A equals B, then f is not 1 to 1. What if I ask you, is f of x equals 7 1 to 1? Is that 1 to 1? So, we suppose f of A equals f of B. Well, f of anything is 7, so 7 equals 7. That doesn't imply A equals B. I mean, what you could say is f of 2 equals 7, and f of 3 equals 7, but 2 and 3 are not different, not the same, so f of x, it is not 1 to 1. I found f for two different numbers that gave me the same y value. If you were to graph that, f for 2 is 7 and f for 3 is 7. There might be other points on this graph. In fact, there are. But at this point, I don't really care, because I can find a horizontal line that crossed the graph in two places. That function is not one-to-one. In fact, the graph is this horizontal line. But again, it could have just been this graph. If somehow you come to know that f for 2 and f for 6, f for 2 equals f for 6, that implies that f is not one-to-one. I found f for two different numbers that give me one y value. Whether it's 11 or the square root of pi, doesn't matter. Now we're going to talk about inverses. Inverses is a function that undoes what the function is. Suppose, for example, after a long calculation, you had the number 17 in your calculator. You made many calculations. For the last 2 hours, you've been making calculations. You get up to 17, and then by error, you multiplied by 2. So now your calculator says 34. And you're like, oh no, I meant to add 2, not multiply by 2. Or I meant to multiply by 37. I didn't mean to multiply by 2. So what you should do is divide by 2. So basically you want to get back to 17 so you can do what you meant to do. You meant to add 37. But right now, when your calculator said 17, you multiplied by 2. Now your calculator says 34. Well, to undo multiplying by 2, you divide by 2. And that will give you the 17. And then you can do 17 plus 37. Okay, this is really just calculator math. How do you get back to what you started with, like, in case you made a mistake? Suppose I told you you have a number in your calculator, you multiply it by 3, and then you add 5. How would you get that number back? Now, how I would do this problem is, I'd see how I get this. First, you have a number, you multiply it by 3, and then you add 5. And then you get 3x plus 5, or f of x. Now, call this value big X, and then undo it. To undo adding 5, you take away 5. So now I have x minus 5. To undo multiplying by 3, I divide by 3. X minus 5 divided by 3, that's the inverse. It'll undo what you did. If you had the number 11, and by accident you multiplied it by 3 and added 5. So your calculator now says 38. 33 plus 5 is 38. Well, this rule says take that number, 38, take away 5 and divide by 3. Well, 38 minus 5 is 33. Look at this. I do get back that original number. I do get back to 11. So if by mistake you have a number in your calculator like 11 and you multiplied it by 3 and then added 5, this is the rule you do to undo it. Take that number that you got at the end, plug it in there, and you'll get back the original input. Okay, f of 11 is 38. But you know what? F inverse of 38 will give you back 11. And if you don't believe that, now f inverse is just the name of a function. It's not f, it's not g, it's not h. It's f to the negative 1. It's just the name of a function. Okay, so if I take f inverse of 38, and we just did this. F inverse says take away 5 from the number that's in the brackets, divide by 3. You get back 11. So now you can do what you meant to do. Instead of multiplying 11 by 3 and adding 5, you now can undo that, get back 11, and do whatever you want to it. Whatever you meant to do. If you have that f of x is 2x plus 5. Well, let's see how you get 2x plus 5. You take x, you multiply it by 2, that gives you 2x, and then you added 5. That's what you did to this number. You multiplied it by 2 and then added 5. And that's f of x. Now after you multiply x by 2 and add 5, you get a new number. Call that x. Now to get back to the beginning, to get back to that number, you take away 5. So it's x minus 5. Sorry. You take away 5, so now you have x minus 5. And instead of multiplying by 2, you divide by 2, and you get x minus 5 over 2. And this is the inverse function. It undoes that. If you have f of 6, that's 2 times 6 plus 5, 12 plus 5, 17. Okay, so you had 6 in your calculator, and by error, for example, you multiplied it by 2 and you added 5, and now you have that number. How do you go from that number back to 6? Well, by this rule. F inverse of 17. You take away 5 from what's in the brackets, that gives you 12. Divide by 2. Look at that. You got back what you started from. You got back to 6. So now, in case you made an error, you could start again. You can say, you know what? I didn't mean to multiply by 2 and add 5. Maybe I meant to multiply by 5 and add 2. Okay. So now you have the right answer. Whatever you do after doing 3 hours of calculation and you get a number like 6, and then by accident you multiply it by 2 and add 5 and you get 17, that's the number in your calculator. And you say, oh man, I didn't mean to multiply by 2 and then add 5. That doesn't mean you have to start from the beginning. You can take the 17, take away 5, get 12, divide that by 2, and you get back to 6. It just undoes everything. If it turns out that f of x is 6, f of 3 is 6, then f inverse of 6 is 3. Now, you can only talk about inverses if the function is 1 to 1. Because there might be other numbers that I can take f of that gives you 6. If I tell you f for 5 is 6, then f inverse of 6 is 5. Well, now remember, f inverse is just another name for a function. Let's call it g instead. We can't have g of 6 being 3 and g of 6 being 5. This is not a function. Okay, g or f inverse, well, f of x must be 1 to 1. It must be 1 to 1. You can't take f of different numbers and get back the same number. For the inverse to exist, the inverse is a function. So before you can even talk about finding inverses, you have to have a 1 to 1 function. For example, if f of x is x squared, this is not 1 to 1 because it fails the horizontal line test. We know that f of 2 is 4. Well, if there was an inverse, that would mean f inverse of 4 is 2. But wait a minute. F of negative 2 is 4. Oh, no problem. That would mean f inverse of 4 is negative 2. Wait a minute. We can't have a function evaluated at 4, whether its name is f inverse or Harvey. Whether it's f inverse of x or Harvey of x. Doesn't matter. Or f of x or g of x or alpha of x. Doesn't matter what we call the name of the function. You can't evaluate a function at 4 and get back 2 answers. That would mean f inverse, in this case f inverse, is not defined. Why was it not defined? Because f itself was not 1 to 1. So before you talk about inverses, you have to have a 1 to 1 function. So if I tell you f of x is 1 to 1, if f of 5, if f of 5 is equal to 13, then f inverse of 13 is 5. To show that two functions are inverses of one another, we have to verify the following. To show that f of x and g of x are inverses of one another. Now, I could have called this f inverse of x, but that would be saying that g of x is f inverse and there's nothing to show. But this is basically how you test to show that two functions are inverses of one another. The first thing you have to show is that when you compose f with f inverse of x, you get back x. And 2, if you compose it the other way, you also get back x. Okay, so how would we show that f of x equals 2x minus 5 and g of x is x plus 5 over 2 are inverses? You don't have to say of one another. Well, we have to verify these two things. So we need to compose, say, f in, well, let's do f first. No, let's do it like this. F inverse of f of x. Well, by definition, this is f inverse of f of x. And that's f of x. So it's f inverse of f of x. So basically, you have x in your calculator, and you compute f inverse, which is this. But, sorry, I think I said that wrong. You have x in your calculator. You have the number x in your calculator, and then you go and you compute, here's x in your calculator, you compute f of x. That is, you doubled x and you took away 5. Now, f inverse is supposed to undo this. And the question is, do you get back x? Well, what is f inverse? Oh, excuse me. We called it g. I apologize. We called it g. We called that name. Again, it's just a name. We called it g. Now, what does g do to what's in the brackets? It adds 5 to it, and then it divides by 2. Okay, so I take what's in the brackets, I denote I'm adding 5 to it, I take away 2. Well, minus 5 plus 5, or 5 minus 5 is 0. So basically we just have 2x over 2, and what do you know? That is x. It did work. But now you have to verify it the other way. So this is f of g of x. It's f of g of x, which is x plus 5 over 2. It says so right here. Now, what does f do to what's in the brackets? It doubles it, and then takes away 5. Okay, I don't care what's in the brackets. I'm going to denote that I'm doubling it, and then take away 5. The 2's cancel out. So I get x plus 5 minus 5. Hey, what do you know? That's x. So yes. So f and g are inverses. We verified that. Suppose I were to tell you to verify the following. F of x is x minus 3 over 4, and g of x is 4x plus 3. Show that, or verify that these two are inverses of one another. So first we'll say look at the Fogg function. By definition, this is f of g of x, and I know what g of x is. So it's f of whatever g of x is. Now I have to take f for something. Well, whatever is in the brackets, I take away 3, and then I divide by 4. Okay, so what's in the brackets, I'll denote that I'm taking away 3 and dividing by 4. 3 minus 3 is 0. 4x plus 0 is 4x. And then we divide by 4. Whoa, we get x. Looking good. But now, what about the other way? The gof of x. This is g of f of x. F of x is whatever it is. It's x minus 3 over 4. Now, we need to take g of that. What does g do to x? It multiplies it by 4, then it adds 3. Okay, I'll take what's in the brackets, I'll denote that I'm multiplying it by 4, then adding 3. This term, the 4's cancel, you get x minus 3. Don't forget to add the 3. And you get x. So yes, you should write this. So yes, f and g are inverses of one another. Now, suppose I told you that f of x is x squared, and g of x is the square root of x. Now, are these inverses of one another? Well, let's see. If you compose f of g of x, that's by definition f of g of x. It's f of anything that equals g of x, which I'm told is square root of x. And what does f do to what's in the brackets? It squares it. Well, if you have the square root of x and you square it, you get back x. Looking good. Let's go the other way. G of f of x. Well, this is g of f of x. Well, f of x is x squared. Okay, so it's g of x squared. What does g do to what's in the brackets? It takes the square root of it. Ooh, the square root of x squared is not x. For example, so if I replace x with 5, the square root of 25 is 5. So x was 5, and that's what I got back. But what about if I plug in for x -6? And I square it, and I get the square root of 36, which is 6. I plug in -6, I get 6 back. I plug in 5, I get 5 back. Well, you know what? The absolute value of 5 is 5, and the absolute value, the absolute value of -6 is 6. Basically, the square root of x squared is the absolute value of x. This is not x. This is why you have to check it both ways. Now you may say, well, what went wrong? F of x, real quick answer, f of x is not 1-to-1. F of x is not 1-to-1. You can't find the inverse. The inverse of x squared is not x. Sorry, is not the square root of x. Okay, now, if I had said that x is at least 0, that removes this half of the graph, and then it does pass the x squared, where x is only positive. It does pass the horizontal line test, and since x is positive, yeah, the absolute value of a positive number is just that number. So if I include that x is at least 0, then f and g are inverses of one another. If I remove that constraint, then they're not equal to one another. This does not equal x all the time, not when x is negative. And for the record, you can't even compute g of a negative number. The square root of -3 is not a real number. So you have problems there either way. So you have to verify condition 1 and 2. You have to compose the two functions in both orders and see if you always get back x. Now, suppose you want to find the inverse for this function. How would you find the inverse of 3x minus 5? Like I said earlier, you start off with x. You have a number in your calculator, and what did you do to it? You multiplied it by 3. That gave you 3x. And then you took away 5, and it gave you a whole new number. First you had x in your calculator, and now you have 3 times x minus 5. How do you get back x? Well, for the record, that last entry is f of x. It said so right here. Well, if you call 3x minus 5 the number that you see in your calculator right now, in other words, if x is, let's stay away from so many 3's. If x is 2, you multiply it by 3, you get 6. You take away 1, you get 5. So 2 became 1. You had 2 in your calculator, you did things to it, and now it's 1. So you want to take 1 and undo what you did to the 2 to get the 2 back. That is, instead of to undo taking away 5, we'll add 5 to this. So we get x plus 5. To undo multiplying by 3, we're going to divide this by 3. And you get x plus 5 over 3. That is f inverse. And if you don't believe it, that's fine. Don't believe it. But verify that this equals x. Verify that this equals x. And once you say yes to both of them, you say, yep, if f of x is 3x minus 5, f inverse of x is x plus 5 over 3. What if you have the function g of x is equal to 1/2 plus 2? Well, if you have x, which by the way is x over 1, and then you take the reciprocal of it, you'll get 1 over x. And then you add 2. So you have 1 over x plus 2. And what you just ended up with is g of x. And now we're going to undo what g just did. So call this, the number in your calculator, x. And to undo adding 2, you take away 2. So you have that, take away 2. Now, if you take a number and you take the reciprocal of it, to undo that, that is, to get back that number, you take the reciprocal again. And look, we got back what we wanted. So, to undo taking reciprocal, we take the reciprocal. So this becomes 1 over x minus 2. And this here is g of x. Sorry. We could call it g of x, but let's denote that it's the inverse. Okay, to undo 1 over x plus 2, you just do 1 over x minus 2. Now one may say, and this is interesting, call it h of x. Oops, I have one typo here. Sorry. I called the function g, so the inverse should be called g inverse. Now, suppose you have f of x is 1 over x plus k. Notice k was plus 2. And now it's x minus 2. Will h inverse of x be 1 over x minus k? Well, we can verify that, whether it's true or not. let's compute h. You start with x, you take the reciprocal, and then you add k. This is 1 over x plus k. That's h. Now, let's call that x and undo it. First, instead of adding k, we take away k. So we get x minus k. And then to undo the reciprocal, we take the reciprocal. And yeah, I never realized that before. There it is. And we proved it. So if I give you that j of x is 1 over x plus 23, then j inverse of x will be 1 over x minus 23. I know that. We just proved it. What about if instead of plus k, what if it were minus k? Is our answer down here going to be 1 over x plus k? That is, the sign changes like it did before. What do I mean by before? It used to be plus k. Now in the bottom it's minus k. So let's see. To build this up, first you take the reciprocal, that gives you 1 over x, and then you take away k. You get 1 over x minus k. This is g of x. What will the inverse be? Let me just move this over a drop. And let's see what the inverse will be. Call this x. To undo taking away k, we add k. To this, we have x plus k. And to undo taking the reciprocal, we take the reciprocal. And we get 1 over x plus k. So yeah, if this says 1 over x minus some number, notice the minus k is not in the denominator. But here, it goes in the denominator, and it becomes 1 over x plus k. That's pretty nice. Okay. So, let us do a couple of more of these problems. Suppose I tell you that h of x is equal to the cube root of 3x plus 5. And I say, find h inverse and verify. Find h inverse of x and verify that it's correct. Okay, so let's build this up. We start with x. Now, if I ask you what h or 7 is, hopefully the first thing you would do is multiply 3 by 7, and then add 5, and then compute the cube root. So let's do the same thing. I'm just not saying 7, I'm calling it x. First, you multiply by 3, that gives you 3x. Then you add the 5, that's 3x plus 5. And then you compute the cube root of it. Cube root of 3x plus 5. So what we have now is h of x. Now call this x, that's the number in your calculator, and undo it. To undo taking the cube root, you cube this, so you get x cubed. Undo adding 5, you take away 5 from that. So now you have x cubed minus 5. To undo multiplying by 3, you divide by 3. So you get x cubed minus 5 over 3. And if we didn't make a mistake, that's f and h inverse. Okay, so unless we made some mistake, we found h inverse of x, and you know, maybe somebody doesn't believe you. They say, nah, I think it's something else, or I think you made a mistake. So you verify it. First, we'll compute h inverse of h, of x, which by definition, note the order of h inverse h and x doesn't change. First h inverse, then h, then x. Same order, h inverse hx, h inverse hx. And now h of x is what it says at the very top. It's the cube root of 3x plus 5. Now, what does h inverse do to what's in the brackets? It cubes it, it takes away 5, and then it divides by 3. Okay, I don't care what's inside the brackets. I'm going to cube it, take away 5, and divide by 3. Well, the cube root, if you cube the cube root, you just get what's under the radical. Don't forget to take away 5 and divide by 3. The 5's cancel out to 0. So you have 3x over 3, which is x. Looking good. Now, we do it the other way. This is h evaluated at h inverse of x. But h inverse of x is x cubed minus 5 over 3. So this is h of h cubed minus 5 over 3. Now, what does h do to what's inside the brackets? There it is, what's in the brackets. It multiplies it by 3 and then it adds 5. And then it takes the cube root. Okay, so first, I'm going to take what's inside the brackets. I'm going to multiply it by 3 and add 5. And then I'll take the cube root. The 3's here cancel. So you have x cubed minus 5. But then you add 5. Well, that's cube root. So it's the cube root of x cubed. But that is x. What do you multiply by itself 3 times to give you x cubed? Answer, x. So I verified it both directions. This equaled x and that equaled x. So there's no question about it. Okay, let us try another one. Suppose you have that f of x is x minus 2 over x minus 4. Now, there's no way to build this up. I mean, I can start with x and then take away 2. So now I have x minus 2. What do I do next? You may say, well, it's obvious. You divide by x. Okay? So now I have x minus 2 over x. The problem is, if I now take away 4, I'll have x minus 2 over x minus 4. This is not x minus 2 over x minus 4. Okay? 20 over 4 is 5. 5 minus 4 is 1. This is not 20 over 4 minus 4, which you can't even do. You can't even do that. I mean, I could have put 5 here. 20 over 5 is 4. Minus 4, I get 0. But you can say, oh, I know what to do. The minus 4 goes in the bottom. No, that gives you 20 over 1, which is 20. 20 doesn't equal 0. You can't do that. Okay, so what can you do? Well, there's two methods. You can do the long division. One way of doing it is to take away 2 from the top and add 2. And what that does is, this becomes x minus 4 plus 2 over 2. Sorry, over x minus 4. So you can divide this. You get x minus 4 over x minus 4 plus over x minus 4 plus 2 over x minus 4. This, of course, is 1. So you have 1 plus 2 over x minus 4, which for the record is the same as 2 over x minus 4 plus 1. This I can build up. I start with x. I take away 4. So now I have what's on the bottom. But I need to get it on the bottom. So I take the reciprocal. There's an understood 1 there. I take the reciprocal. And then I multiply it by 2. So I get 2 over x minus 4. And finally I add 1. And this here is f of x. Looks a little bit different than this, but that is what it is. So now I call f of x, x, big X, different x. And to undo adding 1, I take away 1. So I get x minus 1. To undo multiplying by 2, I divide by 2. So I get this divided by 2. To undo taking the reciprocal, I take the reciprocal, and I get 2 over x minus 1. And to undo taking away 4, I add 4. So I get 2 over x minus 1 plus 4. That's the inverse. This here is f inverse of x. Now, just want to review this again. If you have x minus 2 over x minus 4. If you take away 2 from that, you'll have x minus 2, x minus 4. But to justify it, you add 2 over x minus 4. Well, you can put brackets around that. That gets divided by x minus 4 plus 2 gets divided by x minus 4. If you don't believe that, don't look at any of this. We're adding over here 2 fractions and they have the same denominator. So we keep that denominators and we add the tops. X minus 4 plus 2. But that's x minus 2. Take away 4 plus 2 is minus 2. That's exactly what we started with. And the reason we did this is because this first fraction is just 1. And there it is. Now, there's another way to do this. You could always interchange x's with y's and then solve for y. So if they tell you f of x is x minus 2 over x minus 4, another name for f of x is y. So they tell you this. And now you interchange x with y. Okay, make believe when you were, I don't know, in first grade and your teacher said, I'm going to teach you now how to write y. And that's how you write y. And I'm going to teach you how to write x. And that's how you write x. So, this becomes x is equal to y minus 2 over y minus 4. Now we solve for y. The first thing I would do is try to get all the y's in the numerator by multiplying by y minus 4 on both sides. The right side, no more denominators with y. Distributing, you get yx minus 4x. These are the pieces. Things that are being added and subtracted are the pieces. This piece has a y and this one has a y. So I'm going to bring them all to the same side, say the left side. If you move one of these pieces across the equal sign, all that happens is you change the sign of it. I'm not going to move the yx, but I am going to move the minus 4x because I only want x's on the left side. When I move it to the other side, it becomes plus 4x. The y, ooh, that's a y. I need to move it to the left side. And it's understood to be positive y or plus y because there's no sign. Just like 3 means positive 3, y means positive y. Even if y is negative, it's still that. Because if y is negative 7, that equals positive negative 7. A positive times a negative is a negative. So it moves over to the left side is minus y. The minus 2, it stays on the right side because I only want y's on the left side, and 2 is not a y. So it stays minus 2. Now I'm going to factor out y from the left side. Y times x gives me yx minus y times 1 gives me y. And this is 4x minus 2. Since I want y alone, I'll divide by what y is being multiplied by. And I get y is equal to 4x minus 2 over x minus 1. One last thing is I called out y inverse. Now, you may say, but give me one moment, please. You may say, but wait a minute, that's not what you got over here for f inverse. Well, maybe it doesn't look the same, but let's see if it is. If I multiply this fraction by x minus 1 over x minus 1, I'm allowed to do that because x minus 1 over x minus 1 is 1, and multiplying by 1 never causes any problem. Why did I do that? Because now both fractions have the same denominators. So I add the numerators. 2 plus 4 times x minus 1. So you get 2 plus 4x minus 4. 4x minus 4 over x minus 1. I'll write the positive 4x first. 2 minus 4 is minus 2 over x minus 1. And I bet you that's what I have in the bottom here. Yep, there it is. Now, how can you get the bottom look like the top? So I can factor out a 2. What do I want now? Okay. So I can factor out a 4, and I get x minus a half, because half for 4 is 2. Hmm. 4x minus 2. Okay, I'm going to do it slightly differently. I'm going to factor out the 4, and I'm going to force x minus 1 there. So that's 4x minus 4. So the 4x is good, but no on the minus 4. Should only be taken away 2. But I want to take away 4. So I add back 2. And then I divide by x minus 1. And the nice thing when I do that is I can split it up like this. This reduces to 4, and I get 4 plus 2 over x minus 1. And in case up above, I have 2 over x minus 1 plus 4. That will be fine. Yep, 2 over x minus 1 plus 4. They're able to make them look alike both ways. This method of interchanging x and y is not easier. I assure you of that. It's not easier. If you have y is equal to 3x plus 4, I would take x, multiply it by 3, and then add 4. So now I have 3x plus 4. Then I'd undo that. I'd take away 4, get x minus 4. Undo multiplying by 3, you divide by 3. X minus 4 over 3. If you have y equals 3x plus 4, you interchange x's and y's, solve for y. That's the only term that has y. And I'm going to keep it on the right side. Right side, yes. So x stays where it is. 3y stays where it is. The plus 4, and not being a y, I bring it to the other side. And then I divide by 3, and I'll write y first on the left, is x minus 4 over 3. And then you have to remember to call it y inverse, just like over here, I should call it y inverse. Okay. Now, let us talk about how you graph the two. If this here, so, okay. I'm going to draw the line first. The line y equal x. So line y equal x. The x-axis, the y-axis. If you have this curve here, this is f of x, and you want the inverse, what you think about is the following. Imagine you put, I guess, yellow paint along here. Nice and thick yellow paint, or a heavy coat of it. And then you fold your paper along this line, y equal x. And of course, paint is going to end up over here. Paint is going to end up right there. And that is f inverse of x. They are mirror images of one another. If this is y equal x, and you have a function that touches it and then maybe goes like that, well, when you flip this point over that touched, when you flip it over the line y equal x, it's going to stay right here. That is the inverse is going to look like that. That would be y inverse of x, and this would be y of x. Now, another way of figuring out exactly what the graph looks like, and I couldn't mean exact more than exact. If you want to know exactly what the graph looks like, the inverse. Now, since this graph is 1-to-1, it passes the horizontal line test. This is f of x. Well, do two things. One, interchange x and y. Now, let me make this graph a little bit smaller. So you have this graph. This is f of x. This is the x-axis. This is the y-axis. To graph the inverse, interchange x and y. And then rotate the paper so x is over here and y is over here. Now, this is going to take 2 steps. if you go from front to back, okay, what would happen is the y-axis would be there and the x-axis is still here. And now you rotate your page 90 degrees. So we're not touching the graph at all. We're just playing games with the paper itself. You just flip the paper around. Keep X on the top, and when you rotate front to back, the Y comes here. Now you rotate it 90 degrees clockwise. And what will happen is X will be here and Y would be here. And whatever you see now, that's the inverse. Okay? Remember, you change the labeling of the axes. So maybe I should put them in that color. Now, do you need to remember this and that? It'd be helpful. But maneuver the paper first, interchange X and Y. Maneuver the paper any way you can. So Y is on the top and X is at the right. You might have to look through from the back to the front. But Y is on top and X is on the right, like always. And what you will see is exactly that. Okay, not almost, not close, but exactly that. So this is your sheet of paper. Normally you had X here and Y here. Cross them out. Write X and Y like I have it. And then maneuver their paper in such a way where the pink X is down here and the pink Y is there, and whatever you see, again, since you're at the back and you drew on the front, you're gonna have to look through the page. You're gonna have to draw this so you can see it on the back when you look from the back. And just rotate it so the new X is here and the new Y is there, and whatever you see, that's gonna be the inverse. That's gonna be F inverse of X. So you can see it 100%, and you can draw it on your homework paper, on your exam paper, and no way are you wrong, as long as it's a function. Again, you have X and Y here, cross them out, interchange them, and then move the paper so that first that Y is here and X is there. That's go from front to back, and then rotate it 90 degrees. X will come here and Y will come here, and you will have your inverse. Whatever you see through the page, no need to draw this. No need to draw the inverse. The inverse will be there for you. Okay, rotate the paper 3, 4, 24 times, whatever it takes, to get the X over here and the Y up there. And whatever you see will be the perfect inverse. It never will be wrong. It will be beyond perfect. Okay, so let us try one more. Graph f of x equaling x cubed and f inverse of x. X-axis, y-axis. I think this one is simple enough to do across the line y equal x. So x cubed crosses the origin, goes like this, and it goes like that. Let me just end it here. So the inverse, well, of course, is going to go across 0, because when you flip 0 across 0, it's not going to move. If you cross anything along the yellow line, if this point was on the graph, when you fold it over along the paper along the line y equal x, it's going to stay there. And their image, or the inverse, is going to look like this. Okay, this here is f inverse of x. This here is f of x equaling x cubed. Now, what is the function inverse, f inverse of x? Well, to undo cubing, you have x, you cube it, you get x cubed. Call that x. Now you're going to have to take the cube root of this. And right here is f inverse. F inverse is the cube root of x. So now you know what the cube root of x looks like. And once again, let's do it here. If you have this function, x and y, and you want to find the inverse of it, what you can do is cross out x and put y, cross off y and put x, rotate the paper. You'll have to be looking through the back of it. But if you rotate it so x is here and y is there, I guarantee you what you are going to see is the following. Oh, okay. What you are going to see will be this. Okay, and this is going to be f inverse. Okay, just interchange x and y, and then rotate the paper so x is here again and y is here, and whatever you see, you'll see this. That's exactly the inverse. Okay, that's exactly the inverse. And for example, if it crossed at 2, when you reflect it, you'll see that, not reflected, when you interchange x and y and then rotate your 90 degrees, it's going to cross here. Because this point is 2, 0. When you interchange x and y, you're going to get 0, 2. And if you fold the paper correctly and you interchange x and y, you cross off x and you write y, cross out y and write x, and then rotate the paper or whatever to get y up here and x up here. If the graph crossed 2, 0, it will cross 0, 2. I guarantee that. You'll have the perfect inverse. Do that. Here's your piece of paper. You call this x and y. Initially, you have some graph. Cross these out. Put y and x. Turn the paper around. That is the front to back. And now, through the paper, you're going to still have x here, but now y is here. And it'll even be written backwards. But that's a whole nother story. That's still y, and then you rotate the paper 90 degrees, and you'll have x here and y here. So basically, if you have that for f of x, and you interchange x and y, and then you rotate it 90 degrees, maybe you get that. That will be f inverse of x. You're going to have to look through the paper, because this here was the front, but now it's the back, which you rotated 90 degrees, which still makes it the back. So you're going to have to look through the paper and see what you see. And they will be, that what you get here will be the perfect inverse. Don't get these problems wrong when all you have to do is you have x and y, cross out x, put y, cross off y, put x, rotate the paper from front to back. That will put y here and x there. And then you rotate it 90 degrees clockwise, and the y will come here and the x would come here. Or do whatever you want. Take 10 steps instead of a couple or 3 steps. Take 10 steps. Just get the x here and the y up here. And then whatever you see through the paper, if this is what you see, wonderful. That's f inverse. This completes this section on inverses and one-to-one functions. Good luck with this stuff. Thank you.